Okay, so in the previous video, we looked at E and how ES's limit as n goes to infinity of 1 plus 1 over n to the n. And it's not super important to really be able to understand this thoroughly. But what I want to get at here is that as n goes to infinity, this means n is getting really big. So instead of compounding monthly, which would be 12 times a year, or compounding weekly, which is 52 times a year, what if we were compounding every second, or every half of a second, or every quarter of a second? Then we're talking about hundreds of thousands of times we would be compounding each year. So if n gets really, really big, what we would be talking about is compounding continuously, just over and over and over and over and over again. Okay, so when we are involving E there, we get a continuous growth rate. And our continuous growth rate, we're using the letter K to represent that. And so previously, when we've looked at our kind of generic exponential functions, we've used Q is equal to AB to the T. And if we're wanting to use a continuous growth rate instead of it like an annual growth rate or something like that, we're going to replace B with E to the K. So this Q equals AB to the T becomes A times E to the KT. Okay, so that A still has the same function. It's still our initial or starting value. It's still the y-intercept. But now we replace B with E to the K, so we get this continuous growth rate, or continuous decay is also a possibility here. And the way that we know whether we have growth or decay is going to depend on, first, if A is positive. So if A is greater than 0 and K is also greater than 0, then Q is an increasing function. Right, so we get growth here. If K is less than 0 when A is positive, then our function is decreasing, which means we get that decay going on. Okay. All right, so let's look at a couple problems using this formula. We're going to write an equation and then answer the question that goes with it. So number 3, a population increases from 7.3 million people at a continuous rate of 2.2% per year. Anytime you see that word continuous, you're going to use E in your equation. Okay, so if it doesn't say continuous, it's highly unlikely you would be using E. So our equation, let's use P for the population. I get 7.3, so we'll measure this in millions. So my A is 7.3, and this is E to the KT. So my K is this 2.2% that I need to convert to a decimal. So 0.022T is going to be my equation here for this population model. And then estimate graphically when the population reaches 10 million. So in other words, we're looking to graphically solve 10 is equal to 7.3 e to the 0.022t, and we want to solve that for t. Okay, so we'll do that graphically, which means we'll get an approximation, not an exact answer, but an approximation, which will be just fine. So let's switch over to our graphing program. Okay, so here I've already graphed our 7.3 e to the 0.022x. And what we're wanting to do is find out when that's equal to 10. Okay, so we're looking for a y value of 10. So if I plot y equals 10 on here, see if I can need a y equals there. All right, so there's y equals 10. So I'm looking for where this exponential function is going to cross. And conveniently, this program puts a dot there for us. So we see that that happens at about 14.3 years. Okay. So we'll write that down, and that's all we need to do. And let's go back and take a look at number 4. All right, for number 4, you drink coffee containing 100 milligrams of caffeine, which leaves the body at a continuous rate of 17% per hour. How much caffeine is left in the body 8 hours later? Okay, so let's start by making our formula here. So the amount of caffeine is going to be equal to my starting amount, which is 100. That's my A. And we have continuous, so we know we're using E. And it says it's leaving at a rate of 17% per hour. So that's going to make this negative because the amount of caffeine in your body is decreasing. So we'll turn that into a negative decimal. So negative 0.17 T would be our basic equation there. And then how much caffeine is left in the body 8 hours later? So we'd be looking at A of 8, which is 100 E. So negative 0.17 times 8. Let's see if we can figure out what that is. So I have 100 times, and if you're looking for that button with the E, it's often paired with the one that says ln. A little bit hard to see on here, but that is an e to the x that's just above there. So we'll get the E, and then we're doing negative 0.17 times 8. That gives us about 25.67 milligrams of caffeine left in the body.